Hello and welcome to Noel's Retro Lab. Today we don't have one computer, we have three computers. We have three Commodore 64s right here, and apparently each of them outputs the dreaded black screen. I'm saying dreaded black screen because on a Commodore 64, that can mean that almost anything failed. I know a lot of you have Commodore 64s at home with similar problems, so this should be a particularly interesting episode, because I'm going to go through each of them and I'm going to follow the steps I usually go through to diagnose and repair each of them. We have a lot of work ahead of us. Let's get started. I did a quick test off camera and I thought it was interesting, so I'm going to show it here. I plugged it in, I turn it on, and not only are we getting a black screen, but what else do you notice? The power LED. It's off. So that might mean we have a very easy fix and the switch might be bad or dirty. Just to make sure, I'm using a power protector here, and this shows us that the 5 volts from the power supply is correct and the 9 volt is correct. So it is getting power, but just not to the LED. So this could be a very easy fix. Let's open it up and find out. So we're gonna look at the switch. The switch has 6 terminals right there. When this switch is off, these two are shorted. So the leftmost to the center and the leftmost one. So there you go. And there you go. And the other two are not. Right. And right. And when I turn it on, now these two should not be shorted. And if all goes well, these two should be. It is. And it is. Okay. So it's definitely not the switch. The switch is working fine. One thing I skipped over in my rush to check the switch was just to have a visual inspection of the board, which I always like doing that. And the board itself looks clean, looks a little rusty there, but it doesn't matter for now, right now. Everything looks fine. One thing I noticed is that if you look at these power regulators, they have little dents in them. So clearly someone has been here checking voltages before. Everything else looks good. So let's go ahead and check some voltages to see what we actually get from the power supply. The 5 volt line is on top, the 9 volt AC line is below, and the 5 volt line does a couple things here with an inductor and a couple capacitors. Then it goes through the switch, and then it goes to the rest of the board. The 9 volt line goes through the bottom rail there, it goes through this inductor, it goes also through the fuse, but us not seeing the LED means the 5 volts are failing, so they're not getting here for some reason. So we'll see where exactly we're losing those. All right, let's start checking some voltages. So we should have 5 volts right here, and we do. Maybe the LED light was bad. Let's check this one right here. No, okay. So there we're only getting 0.4 volts. That's clearly wrong. So following the diagram, we should also have 5 volts right there. And we don't. 5 volts here before the inductor. We do, and after the inductor, we don't. So maybe this inductor is bad. So inductors should be short when there's no voltage differences. So if we test this for resistance across the inductor, we should hear the beep and get a short, but we're getting some resistance, not too much. Looks like it's only 62 ohms. But that doesn't look right. That might be enough to make this whole circuit not work correctly. So before we replace that inductor, I was looking at it a little bit more closely, and it almost looks like it's not well soldered in. It doesn't have enough solder there. So I wonder if that's part of the problem. Let's give it a quick reflow, and if not, since this is only for filtering the 5 volts line, we could just short it for now. Just put a bridge and just to see if things work. All right, now let's check continuity across the inductor. Oh, oh wow. So maybe that fixed it. Let's try it. Let's turn it on again. And let's measure 5 volts directly where the LED would be. There we go, almost 5 volts. That's good enough. So let's see if we get any kind of image. All right, let's give it a try. It's plugged in. We turn it on. And nothing. Looks like it's still a black screen. All right, I'm not too surprised. So the next step would be to check voltages on the board and make sure everywhere we get the correct voltages. And especially want to check those two over there since they have those suspicious marks. This voltage regulator here is the 7805. It generates 5 volts. So this is the output. This is the ground. So let's check the ground. Yep. And the input should have something around 9, 10 volts. There we go. And the output should be 5. Yeah, that's spot on. And this one over here is a 7812. This generates 12 volts DC. So the input, 19 volts, and the output, yep, 12 volts. Okay, so yeah, those work fine, even though I was a little suspicious of those. So let's also check on the other side of the board, which is fed primarily by the 5 volts that comes straight through the power supply. And let's check one of the faraway chips like this CIA over here. I know it's pin 20, should be 5 volts. And yeah. So I would say voltages are fine on the board. So we need to figure out why we're getting this black screen. So in this area under the metal shielding, we have the VIC chip, which generates the video. So that could be one of the reasons why we're getting no video out. We also have the clock circuitry, which generates a clock signal for all of the board. Those are probably the next two things I want to check. So let's pop the lid off. So first of all, let's check that the VIC chip is getting the correct voltages. So pin 40 should have 5 volts. Yep, there you go. And pin 13 should have 12. Yep, so that looks good right there. The clock signal is generated around here from the crystal oscillator, but let's check it all the way on the CPU. If it gets there, then we don't have to worry about checking anything here. If not, we'll have to backtrack and see where the problem is. That's actually a fairly common problem that I've encountered with Commodore 64. Some of these chips fail, and then the system just doesn't have any clock signal. So let's turn it on and spin number 1. And it looks like we have a healthy clock signal, exactly almost 1 megahertz. So that's not it. One final test before we get into anything more complicated is to remove the SID chip. The SID chip is not necessary to start the system, and it sometimes can be a cause of problems. So let's remove it. It's socketed, so it's really easy. All right, and now let's turn it on. Yep, still nothing. So before we go any further, let's do some sanity check on the board and make sure that the signals are correct. I'm specifically going to be looking at the data bus and the address bus and maybe some of the other signals that show general health. So let's start with the address bus, which should be pins 7 through 20 something. So this one should be, okay, yeah, that looks like general address bus activity. Looks pretty good. Yeah, that's fine. The data bus on the CPU, so it should be that, yeah. Okay, yeah, that looks generally fine. The read-write should be 38. Oh, there's nothing there. So that one is constantly high. So that tells me there's something not quite right. It doesn't mean that the CPU is bad, but obviously there should be some activity there. What about Q and ready? It's 3. No, and ready. So yeah, there should be some activity there. Let's check the VIC chip as well. So let's look at specifically at the sync signal. That is pin 15. This should be sync. That's more or less what I would expect for a blank screen. So at least that's not putting that correctly. And then the color signal should be in pin 14 right next to it. Yeah, that's correct for a blank screen. Looks about right. At this point, we don't have a clear suspect because everything looks more or less okay, even though some of the activity isn't quite right. So we move on to trying the dead test cartridge. This is a cartridge that will hopefully tell us some information about what's wrong, even if there's some hardware that is failing. Now, it's possible that we may still get a blank screen, and I believe that only happens if either the VIC chip, CPU, or PLA are bad. Otherwise, we should be getting some information. So let's try it out. I'm gonna turn it on. Now, it's normal that it stays blank for a few seconds, and then a blue screen should come up. Or we should get some flashes to indicate that there's something wrong. But we are getting nothing again. So that really narrows it down, most likely to CPU, PLA, or VIC chip. The VIC chip, the output signal from the VIC chip seemed okay, the sync and the color signal. So that's probably not it, but this one is socketed. So this is the easiest one to try first. If not, my guess would be on the PLA is something that fails quite a lot, and it's unfortunate because it's a hard chip to come by. So let's start trying those on a board that we know works. That way we can completely eliminate them if the board continues to work correctly. So this is a working Commodore 64 from my own collection, and we're going to use it to try the VIC chip from the other computer. It actually helps immensely to have a working version of the computer you're trying to repair. Whether it's to swap out chips and try them to make really sure, or even to compare signals. I do that a fair amount of the time. If I'm not sure that a computer is behaving correctly, I will bring one that works and look at those signals and see what kind of output I'm getting. And that really helps diagnose things a lot. So as much as possible, if you're into this kind of thing, I recommend that you have at least one working version of the computer you're trying to repair. First of all, let's just turn it on and make sure it works as we expect. Otherwise, we'll throw off things. Okay, there you go. And so now we're gonna swap out the VIC chip just because it's the easiest one, although I really think that it will probably work based on the signals that we were seeing. The VIC chip from the other computer it's in, let's turn it on. And yeah, it works. Okay, so we've definitely eliminated that. So the next thing will be to desolder the PLA from the other board and try it in this one. That's the PLA right there. And we start desoldering with the desoldering gun. After that, I like to pass the soldering iron without any solder and just push the pins a little bit to make sure they're loose. And now the PLA should come straight out. Yep, just like that. All right, time for a new socket. Sorry about the camera angle. It's pretty hard to see anything, but I'm just soldering it back. Now I scrub with some alcohol to remove all flux residue. And I use a rag to soak up the alcohol with the flux and leave the board really clean. I've already popped in the new PLA on this board, so let's try it out. And okay, this one seems to be working as well. So it was not the PLA. That probably leaves the CPU, so let's try that next. All right, so I just saved you the whole desoldering and resoldering the socket. That was just like the PLA. And we have the new CPU on this board. Let's turn it on and try it out. Wow, so it works still. All right, well, that makes things a little bit more difficult. So we know it's not the VIC chip because we've tested that. It's not the PLA, and it's not the CPU, and it's not the SID chip because we've removed that. It's not the voltages because they all seem correct. So we may have to have a look at the board itself, make sure the buses are correct, that there are no shorted lines, for example, that could be preventing the CPU even from reading data correctly. So yeah, we have some more investigating to do. Here's the plan. Before, we just looked very briefly at some of the signals on the board to make sure there was activity. We know the clock signal looks okay, and we know that roughly the data buses were fine. But now we know there's something definitely wrong in there, and it's not the chips. So I'm going to go one by one through all the bits in the address bus and the data bus, and then in some of the other bits as well, like for example, the addresses that are generated for the RAM itself from the PLA, and some of the special signals coming from the CPU. If all that looks good, the next step would be to look at some of the ICs on the board that are related to those three main chips. So just because the dead cartridge is not working doesn't mean, as you saw, it doesn't mean that it's just the fault of one of those chips. It could be one of those ones that is related to them and is preventing them from working effectively. And in particular, I'll look at the ones that, when failing, could cause a black screen, and the number one suspect of those are going to be the ones that were MOS branded. Those have a much higher failure rate than the regular, some of the other regular brands. These I'm not going to look at. Those are the ROMs. I'm going to be doing all of this with the dead test cartridge in, so it ignores the ROMs completely. Those are the CIA that are not preventing the computer from starting up. So this shouldn't be the cause of the black screen. Technically, it shouldn't be the memory, even though that's happened before, and that's why we're going to look at the data bus specifically. I'm going to start with the data bus because it's maybe the most likely one, since it's tied to the input and output of all the RAM chips. And I'm going to test it on the CPU itself because they're all nicely in order. Okay, so data bus is pins 30 through 37. So let's check them all correctly this time. Let's start with 37. Yep. Okay. They all seem fine. None of them are stuck high or low. The next thing, let's look at all the address bits in the bus. And those are starting in 7 and going all the way to 23. Okay. Okay. All the bits in the address bus seem fine. Let's check some of the other bits around the CPU. So before, we had seen that, REQ and ready were low all the time, or were high all the time, or inactive. This is ready. Under normal operation, they should have some activity. Same thing with IRQ. So that's very odd. And read-write should definitely have activity. That's in 38. 38 right there, and it's also totally high. 39 is a clock out. Yeah, that's fine. 40 is the reset line. Oh, reset line is active low. That's what the bar on top means. And this is low. That explains why there's no activity at all in the CPU. The CPU thinks it's being reset all the time. There's no activity. Whatever activity we're seeing on the address and data buses is coming from somewhere else, from the PLA or most likely the VIC chip. That's really good news because this is definitely a problem. Let's look at the circuit and see where the reset signal exactly comes from. So I looked it up, and the reset signal comes from this IC, U20. So this is a 556 timer. So what it does is it holds the reset signal low for some time, probably some milliseconds or a tenth of a second, after the board is powered on, and then it puts the reset signal on high so the CPU can start operations. The output is on pin 9, and then it goes through an inverter. We want reset to be on the CPU. We want it to be high at this point. It is going to go through an inverter, so we want it to be low out of the counter. This should be low, and it's high. Let's turn off the board, and let's turn it on. Yeah, exactly. On a healthy C64 board, what you should see is the signal should go high, and then probably a tenth of a second later, it should go low, so that it goes through the inverter, and then it gets sent to the CPU as a high signal. But this is staying in high all the time. One thing we might want to do before replacing this is to check that all the inputs are fine. 7 should be ground. Yeah, that's fine. 12 and 13 should be somewhere around 5. 8 should be somewhere in the middle from that large resistor. 10 and 14 should be 5. That's it. So it looks like it's correctly hooked up. It's getting the right voltages. It's just not outputting the correct signals. So let's definitely replace it. Let's pop in the new timer. And before we even check video, let's make sure the clock is doing what we expect. And now we're going to turn it on. And so we expect the signal to go high for a little bit and then down again. High and low. There we go. That's exactly what it's supposed to do. And while we're at it, we can check that the reset line on the CPU is high. There we go. Let's try the video output now. Okay, so here's the moment of truth. Let's try it with the video output and see what happens. Wow, there you go. That was it. We had 2 things wrong on this board. We had this inductor, which wasn't soldering correctly, and then we had the timer that failed and left the reset line on low. Let's run the dead test cartridge just to make sure, but this is looking really good. It's normal that it spends some seconds, with a black screen, and right about now, there we go. We should get some more tests. And there we go. It all seems to work correctly. So we fixed one of the 3 Commodores I sent myself to fix in this video. I guess I was a little overly ambitious. To be fair, we could have fixed it earlier had I checked for the reset signal when I did a pass through all the signals. We wouldn't have had to desolder several chips and test them, although it's not a bad thing to have socketed chips in your Commodore 64. So I hope you enjoyed the video and it was useful for those of you trying to fix a Commodore with similar problems. If you liked it, please give it a thumbs up. And if you want to be notified when I release the video fixing those 2 Commodores, then hit the subscribe button and that big blue circle over there. Until next time.